Okay. So maybe we should have done a quick recap of what we did last week. Last week, we were focused on how dense certain subsets of the real numbers are, so in particularly the integers and the rationals, right? Mm-hmm. And the big takeaway from last week is for any real number c, I'm always guaranteed that c to c plus 1, closed on one end, open on the other, contains an integer. And then we proved that both the rationals and the irrationals are dense in R, meaning any open interval you take, we're always guaranteed that there's a rational number in there, and we're always guaranteed that there's an irrational number in there. So that's what we ended with last time. Make sense? Any questions on those two things before we continue?
Yes.
What's up?
Say it one more time. What does it mean for something to be dense on something?
So pick any open interval you want.
Okay.
So pick any two numbers, A and B, such that B is a bigger number than A.
2 and 5.
2 and 5 works. But even if they're really, really close together,
Okay.
even if we're talking about 2 and 2.0000000000001, between this number and this number, I'm guaranteed that there is a rational, there's some fraction that I can write that's bigger than this and smaller than this, and I'm guaranteed that there's some irrational. I can come up with some number over the square root of 2, or some number over a number times the square root of 2, I think is what we did, in between these two. So what we're saying is for any open interval a, b, I'm guaranteed that I can find a rational in that open interval, and I'm guaranteed that I can find an irrational
Okay,
in that
so
open
what does
interval.
that mean? Using the word dense.
That's what it means to be dense. A set is dense in the real numbers if every open interval of real numbers is guaranteed to contain an element from that set. So the integers are not dense in the real numbers. Why? Because I can find an interval, namely 0.5 to 0.6, that does not contain any integers. Therefore, the integers are not dense in the real numbers. But since for any open interval I pick, I always have a rational in there and I always have an irrational in there, then those two sets are dense in the real numbers.
That does not make sense to me.
Look at our real number line. So if we look at an interval, we don't include this point, we include all the points in between, and we don't include this point.
Okay.
We're saying that the real number line, there's always a point somewhere in here that is going to be a rational number, and there's always a point somewhere in here that's going to be an irrational number.
Okay.
That's all. That's
It's
it.
not saying anything though. Especially when it says prove something is dense on something.
How do we prove something's dense?
Show that there's always something in between those two elements.
Okay, but what you just said is we're guaranteed to have a rational and an irrational.
Right, that's what
We're
we proved.
guaranteed every single time.
We proved it, so now we know. We proved that if you take any open interval a, b, that there's a rational in there.
Okay.
Do you remember how we did it? So a, b, let's re-go over the proof real quick. So I got a point A and a point B. How am I guaranteed that there's a rational in between those? What did I do? Well, I said by the Archimedean property, I know that there exists a natural number, n, such that 1 over n is less than b minus a. So in other words, I can find a number 1 over n so that whatever distance that is, we'll say it's that big, that distance is smaller than the distance between these two.
Alright, I remember what that
So here's b, so that means b minus 1 over n is somewhere over here. So here's a, here's b minus 1 over n, here's b. What we did is we proved that there's a rational number in here, and since it's in here, it's definitely in here, right?
Okay.
The way that we proved that is we said, let's scale up our number line basically by n. So I'm going to multiply this by n, this by n, this by n. So we have now an, we now have bn, and now b minus 1 over n times n is going to be bn minus 1. b times n is bn, 1 over n times n is just 1. So then we knew, since we're guaranteed on an interval c to c plus 1 that we always have an integer, I'm guaranteed, notice that from bn minus 1 to bn, that has a distance of 1. I'm guaranteed that there is an integer somewhere from here to here. There's some integer m in here. Come in. What's up?
So sorry to interrupt your class, but can I use Levi for like 30 seconds?
You sure can.
Thank you so much.
Bring him back as good as you take him.
I'll try to.
So, since this is a one integer distance, we're going from bn minus 1 to bn. This is a distance of 1. We're guaranteed that in every distance of 1 we get at least one integer, right? So we're going to call that integer n. Well, if m is between bn minus 1 and bn, then m over n is between b minus 1 over n and b.
So all this is proving is the set of irrational numbers is dense in R. Correct?
The set of rationals is the one that we're doing right now. The set of numbers that can be expressed as fractions. So I just barely said I found some fraction m over n in there. That's what I just found. So, since a over b was an arbitrary interval, in other words, you can follow this procedure for any interval you pick. Pick any interval you want and we can follow this procedure. So if we pick the interval 0.5 to 0.6, what was my procedure? My procedure was find a natural number such that 1 over n is smaller than this distance. Okay, that natural number is 100. That's one of them. There's infinitely many. But notice that 1 over 100 is a smaller number than 0.6 minus 0.5. Right? 0.6 minus 0.5 is 0.1. That's only 1/10. This is 100. Right? So if we go to our real number line, let's erase these, erase these, erase these, and do it again. Here's 0.5. Here's 0.6. This point over here, even though it's not to scale, is 0.6 minus 1/100. Or in other words, 0.5999. Or 0.59, right?
Okay.
So then, to go from here to here, I multiplied everything by n. So this is 0.59 or 0.6 minus 1 over 100. So I scaled up my number line by n. 0.5 times 100, that's 50. This is an. Maybe I'll just keep these down here and put the real numbers above them. This is 50. This is then, not 50. Oh yeah, 50. This is 60. And then this is 50 minus 1, or 60 minus 1. Right? 59 times 100 is 60 minus 1. Or 0.59 times 100 is 59, which is the same thing as 60 minus 1, right? So notice that when I scaled it up by n, 60 minus 1 to 60 is always going to be 1, a distance of 1. So I'm guaranteed that in this interval, I have an integer. In this case, it happened to be right here, but it could have been somewhere in between if I picked different numbers. In this case, it was 59. So then I said, okay, so then 59 over 60 is a number between these 2 points. So there is a rational number between 0.5 and 0.6. And so for any two numbers you pick here, I can always follow this exact same procedure that the proof gave us and find a rational number in between those numbers. Is that making sense, or is this putting real numbers in just making it more confusing?
It's not confusing, I understand that we did that, and that's fine, but with the other ones, let's see. Is there any more that we need to prove like that? Just the rationals and irrationals?
That's it. And those were the only sets we proved are dense in the real numbers. Because we're going to be using that fact down the road.
Right.
Okay. So good there. Ready to move on to absolute value?
Yes, yes.
Okay. Absolute value. You're all familiar with absolute value. You've used it 100 times. But let's go over the definition to make sure that we're very clear on what it is. The absolute value of x is just x if it's a number greater than or equal to 0. And it's negative x if you give me a number less than 0. right? So what's the absolute value of 3? Well, 3 is greater than or equal to 0. So the absolute value of 3 is just 3. What's the absolute value of negative 4? Well, negative 4 is less than 0. So the absolute value of negative 4 is negative 4, or 4. Right? Pretty simple. Now, absolute value is one of those things that has a simple definition, but it's easy to get confused in your proofs when you're throwing in minus signs and positive signs. Because when you're doing proofs with absolute value, negative x could be a positive number, and x could be a negative number. So that's where you're going to get confused. If x is negative 4, then the absolute value of x is negative x.
Okay,
Right?
right.
So just as I'm doing proofs, I'm going to often write negative x and talk about it as a positive number. So don't get thrown off by that.
Wait.
If
If
x is equal to negative 4,
the
then the absolute value of x is negative x, or negative 4.
Okay.
Right?
It always goes positive though.
That's
Yeah,
fine.
so negative x is a positive number.
Okay, but that's not true because if x is 4, negative
No,
x
if
is
x is negative 4,
I'm saying right there. You can't say no down, right there. If x is 4, negative x. That's not right.
no, if x is negative 4, then the absolute value of x is equal to negative 4.
Right, but why did you write that? That doesn't make any sense. Why did you write negative x right there?
This is, if x is negative 4, then the absolute value of x is negative 4, right? Which is the same thing as negative x. Because x is
So it's
negative
just
4.
for negatives then.
Yeah, it's only going to feel weird to you
Why are
when,
you writing that?
when we're taking the absolute value of a negative number. When we're taking the absolute value of a negative number, it's going to throw you off.
It doesn't throw me off.
Okay.
You writing negative x throws me off. Because if x is positive, then it becomes negative.
Right, if x is positive, then negative x is a negative number. But if x is negative, then negative x is a positive number. Okay, so let's do the proofs. So our first proof is we're going to prove that the absolute value of c is less than or equal to d if and only if negative d is less than or equal to c is less than or equal to d. Understand what we're proving? Alright, so let's do the proof. Let C and D in R, draw my arrow first. Let's prove it this way first. Remember, when we're doing if and only if proofs, I need to show that this being true implies this is true, and then I need to show that this being true implies this is true. What's up?
Are you missing anybody today?
Nope.
Okay, perfect.
So first I'm going to show that if this is true, then this is true. So I'm going to let C and D be numbers such that this is true. So 1, let C, D in R such that the absolute value of C is less than or equal to D. Right? Now, C, there's two options for C. C can either be non-negative or C can be negative. And we need to handle the case in both those situations. So, 2. Let's start out with the easy case. If C is greater than or equal to 0. If C is greater than or equal to 0, then the absolute value of C less than or equal to D gives us C is less than or equal to D. Because in that case, the absolute value of C is just C. If C is greater than or equal to 0, if x is greater than or equal to 0, the absolute value of x is just x. Good? Now, let me get my notebook. This is 1.3.
Did you take these notes in a lecture, or did you just go through the book and write down the proofs?
Oh, this was me going through the book. I never went through this book in college.
Oh.
So, last year was my first time going through it, so I just took notes as I went through the book and wrote them down. Okay, so, sorry, I should have finished my thought here first. So, if C is greater than or equal to D, then we have C is less than or equal to D, right?
Wait, you mean 0?
Oh, well, let's go through the whole thing. If C is greater than or equal to 0, then the absolute value of C is less than or equal to D, which gives us C is less than or equal to D, right?
Right.
Because now the absolute value of C is just C. But we also knew that C is greater than or equal to 0, so that gives us 0 is less than or equal to the absolute value of C is less than or equal to D, right? Since D is greater than or equal to 0, negative D has to be less than 0. So that gives us that negative D is less than or equal to C is less absolute. Oh, no, we're done with the absolute value, sorry.
Yeah, that makes more sense.
Is less than or equal to C is less than or equal to D. Okay, make sure that makes sense.
And negative D is less than 0.
Right, we use that fact to get from here to here. Since I know that D is greater than or equal to 0, then negative D is definitely smaller than 0. So I can replace the 0 on this side with negative D because I just went further this way.
Right.
So if C is greater than 0, it's definitely greater than negative D. We good with that case? Alright, 3. Now, if C is less than 0, then absolute value of C less than or equal to D gives us, what's the absolute value of C going to be now?
Negative C.
Negative C. This is where it's always going to feel weird. Negative C is less than or equal to D.
So now you just have to prove that it's greater than or equal to negative D.
Well, we've got to continue, multiply both sides by -1,
Okay.
which is going to give us, then C is greater than or equal to negative D. Make sure I do negative to both sides. Remember, when you multiply by a negative number, flips inequality. That's one of our proofs from earlier. So going from here to here, I just multiply both sides by -1, which flips the inequality. We good up to here? Okay, so I have C is greater than or equal to negative D. Now let's see, how am I going to justify that D is greater than or equal to C though? Oh, so that's forcing negative D to be less than 0. So D is definitely, let me rewrite this one more way. So I have 0 is less than, or is greater than C is less than or equal to negative D, which finally gives me D is greater than or equal to C is greater than or equal to negative D, like that. Remember, I know from the start C is less than 0. So since C is greater than or equal to negative D, and C is less than 0, I have 0 is greater than C is greater than or equal to negative D. If negative D is less than 0, then D is greater than 0. So since D is greater than 0, if C is less than 0, then C is definitely less than D, which also includes less than or equal to D. We just need to get it in this form, so that's why. Is there any questions about what we did there? So now we've shown this way on the implication. We've shown that if this is true, this is true. Now we need to do the inverse. We need to show that if this is true, and then we're done with the proof. So now we'll go the other way. So assume, or let C be in R such that negative D is less than or equal to C is less than or equal to D. Again, we have two cases. We have C is either greater than or equal to 0 or C is less than 0. So if C is greater than or equal to 0, what does that give us? maybe say this, then C less than or equal to D, just looking at this half of the inequality, directly implies absolute value of C is less than or equal to D. Right? Because if C is greater than or equal to 0, the absolute value of C is just C. So this half of the inequality already gave me everything I needed. So now then, if C is less than 0, then I'm going to look at this half of the inequality now. Then negative D less than or equal to C gives me negative D less than or equal to, here's where it's going to be weird, the absolute value of negative, or negative the absolute value of C.
Why is that?
So we'll work at it backwards, look at it this way and see that it's true. Since C is less than 0, what's its absolute value?
It's a negative C.
Negative C. Since C is less than 0, the absolute value of C is negative C. So the absolute value of C is negative C, and then negative C is C. So I just rewrote C. Since I know that C is less than 0, another way that I can write C is just equal to negative the absolute value of C. The same way that if I know that negative 3 is a number less than 0, that's also equal to negative the absolute value of negative 3. Oops. C is a negative number. So C is equal to negative the absolute value of C. Same way that since negative 3 is a negative number, it's also equal to negative its absolute value.
Yeah.
So a negative number is equal to the negative of its absolute value. So a negative number is equal to the negative of its absolute value. We good there now? And then from here, we're just going to multiply both sides by negative 1.
Aren't you kind of skipping, are you skipping any steps here?
What does it feel like I'm skipping?
Oh, never mind. Never mind. I think I see it.
Well, if there's something fuzzy, let's bring it up.
It makes sense.
Okay.
I just was missing it before.
So then multiplying both sides by negative 1 gives us that D, we're going to flip the inequality, is greater than or equal to the absolute value of C. And we're done with our proof. Any questions? Still absorbing? Okay. And while you absorb, I'll start thinking about my next proof.
That makes sense.
Okay. So, while I'm erasing this, so the next proof that we're going to do is that for any real number you choose, call it x, that negative the absolute value of x is less than or equal to x is less than or equal to the absolute value of x. Seems kind of obvious, but this is one of those proofs that might feel weird to say, how do we start? So proof, what am I proving? I'm proving that for all x in R, negative the absolute value of x is less than or equal to x is less than or equal to the absolute value of x. Right?
And depending on what x is,
Doesn't matter what x is.
one of those will be equal, right?
Oh yeah, and it turns out x will either be equal to the left or the right. Yeah. So, how are we going to start this proof?
Let x and r.
Yeah, grab some arbitrary element in R. Okay, now what?
Now you're going to consider the absolute value of x and find out, and then consider if it's negative or positive.
Right, so we're going to look at two cases. Either x is greater than or equal to 0, or x is less than 0. And we're going to show that that's true in either case. Right? If x is greater than or equal to 0, then what do we know is trivially true? We know that this is trivially true. Since x is greater than or equal to 0, maybe I'll write a big inequality here and then a smaller version under it. Then we know that negative x is less than or equal to 0 is less than or equal to x is less than or equal to x. Pretty trivial. A lot of terms in there. I'm going to write it simpler. Negative x is less than or equal to x is less than or equal to x.
Why did you do 4 terms the first time? Oh, because
To fill in the gap of how I'm justifying this to this. And you did it without inequality.
Yes, looks great.
And now, put in absolute values. What's the absolute value of x?
x.
X. So x and absolute value of x are the same thing in this case. Maybe make a note over here. Note over here. X is equal to the absolute value of x in this case. So then I can rewrite negative the absolute value of x is less than or equal to x is less than or equal to the absolute value of x. Right? Since x is equal to the absolute value of x, I can replace any of the x's I want with just absolute value of x. Is that the same thing?
It's so dumb.
Alright. 3. So we handled the case where x is greater than or equal to 0. Now let's do the harder case. If x is less than 0, then, and maybe make our note over here, now negative x is equal to the absolute value of x. Right? So then, let's see how I want to do it. My gut is telling me to do this, but I don't see it all the way through yet. Negative x is less than or equal to negative x. Let's see, negative x is going to be greater than or equal to x, so let me flip the sign. Negative x is greater than or equal to negative x is greater than or equal to x.
Don't you say 0 and then x?
Yeah, we can put the 0 there first if we want. I thought you were ready to skip that.
Oh.
We'll put it there. So that's true, right? Simplify it. Negative x is greater than or equal to negative x is greater than or equal to x.
Put in the absolute value.
Why do you need to have both those negative x's?
Because
Okay, here's how I'm going to rewrite one more time. I think I see it now. Oh no, because I needed an x.
Yeah.
Yeah, we're going to be broken. I need an x when it's all said and done.
proved it. You know that.
I need an x in the middle. I always have an x in the middle. So x, sorry, this is what happened. I should have just looked at my notes first. Make sure I had a high level view of how to do it. Negative x greater than or equal to 0, greater than or equal to x, greater than or equal to x. Simplify negative x greater than or equal to x, greater than or equal to x. Negative x greater than or equal to x, greater than or equal to negative x. Right? Now replace my negative x's with absolute value of x. Absolute value of x greater than or equal to x, greater than or equal to negative absolute value of x. And we're done.
That's not right. Oh. Oh, yes it is.
Yeah, x less than 0, so we can make this substitution wherever we want. Feel good with the proof? We're done absorbing, ready to erase? Okay, so what's next? Okay, so the next one we're proving is the triangle inequality. Some of you might remember that name for a theorem because it's a theorem from geometry. It's the theorem in geometry that basically says the sum of two triangle sides is always greater than the remaining side. Here's what it is in this class. Triangle inequality. For any two real numbers, the absolute value of a plus b is always less than or equal to the absolute value of a plus the absolute value of b. Make sense what I'm saying?
I feel like we've done this before.
We did it in geometry.
Did we? No.
We did it in geometry for sure. And it might have even come up in discrete math.
Maybe.
Or something similar to it, and we were just talking, and I might have just proved it along the way. That's probably what happened. That seems vaguely familiar. Either way, let's do the proof. Alright, so let A, B, and R. Grab any two real numbers. Then we know that negative absolute value of A is less than or equal to A is less absolute value of A and negative absolute value of B is less than or equal to B is less than or equal to absolute value of B. This is just our proof that we just did. I'm just using this twice. Good? Okay. And then I'm going to combine these two inequalities. In other words, I'm going to know that this plus this is less than or equal to this plus this is less than or equal to this plus this. So make sure this makes sense. So I'll put parentheses for the negatives. Negative absolute value of A plus negative absolute value of B is less than or equal to A plus B is less than or equal to absolute value of A plus absolute value of B. You good with that, combining those two inequalities?
No.
What don't you like? So I know that, let's look at one piece at a time. I know that A is greater than negative absolute value of A, and I know that B is greater than negative absolute value of B. So if I take negative absolute value of A, let's just write it out really long for one piece.
Well, that makes sense.
Negative absolute value of A is less than or equal to negative absolute value of A plus negative absolute value of B is less than or equal to A plus negative absolute value of B, which is less than or equal to A plus B, is the way we could write it all the way.
What the frick?
That makes sense.
That just made it more confusing.
Or get rid of that part, just look at this.
It's basically what you just wrote.
I know that negative absolute value of A is less than or equal to A, right? This is less than or equal to this, that's right here. And I added the same thing to both sides.
Okay.
So that's how we got here. And then going from here to here, I know that negative absolute value of A is less than or equal to B. So that gets me from here to here. So I got this is less than or equal to A plus B. That's this side of the inequality, and can do the same thing to get this side.
You just
Do we
cut
need
out-
to see that, or are we good?
You can just cut out the middle part, right? That's basically what you did.
Yeah, so ignore this step now. So we have this is less than or equal to this, and they can do a similar thing to show that this is less than or equal to this, and therefore you get this whole inequality.
Huh.
But it's just combining two inequalities the way you're used to doing it. I think you're used to doing it. I don't know. Maybe you've never done it. You've done algebra with inequalities, right?
Yeah.
No? Yeah? Some have, some haven't? Shoot.
We should, well, I mean, you do it in algebra too. That was a while ago, but.
Yeah. Alright, we'll continue. 4. Okay, so I have that. Let me rewrite this inequality a different way. I'm going to factor out my negative. So I have negative absolute value of A plus absolute value of B is less than or equal to A plus B is less than or equal to absolute value of A plus absolute value of B. How can I make this next step intuitive?
Don't you just use lemma 1.6?
Lemma 1.6? Oh, yeah. I didn't need to do what I was going to say I need to do. You're exactly right. I was thinking wrong. That's exactly right. We're just going to use this lemma now. So, since I know that I have D, I have negative D. What's D in this case? Absolute value of A plus absolute value of B. I have negative absolute value of A plus absolute value of B is less than or equal to some number, doesn't matter, is less than or equal to absolute value of A plus absolute value of B. Then I can rewrite it this way. The absolute value of the number in the middle is less than or equal to whatever this right-hand thing was. So, using that, we can just rewrite it this way. Then, the absolute value of A plus B, the middle part, the absolute value of the middle part is less than or equal to whatever the right-hand term was. That's using our very first proof that we did today. Questions? Anything weird?
Wait, what did you do? I'm so confused.
So, let's rewrite this line down here. If I let D equal absolute value of A plus absolute value of B, and let C equal A plus B, then I can rewrite this line like this. Negative, what did I use? D. Negative D is less than or equal to C is less than or equal to D. If D is listing and C is listing, then rewriting this line is right here.
Oh, I
Negative
see.
D less than or
Oh,
equal to C less than or equal to D.
Right.
Then we can use our theorem up there, which means that this is true. Absolute value of C is less than or equal to D. Plug in what we knew C and D were. That means the absolute value of A plus B is less than or equal to absolute value of A plus absolute value of B. Using this theorem. Good?
Yeah.
Awesome. Okay. So, three different useful ways to write the exact same thing. If we have A and R as numbers, the absolute value of x minus A being less than R, we can rewrite this way, and we can rewrite this way. So let's quickly show that. So I'm going to start with absolute value of x minus A is less than R. This isn't so much a proof as he just notes these three are all equivalent. So how can we rewrite this? Using this formula, we can rewrite this as negative R is less than x minus A is less than R, right? That's just using this. Absolute value of something less than or equal to something just gives you this.
So the lemma doesn't exactly use the less than sign, but I see how it still holds. When can we and when can't we switch out a less than or equal to for a less than sign when using lemmas and theorems?
Oh, I see what you're saying. Yeah, I didn't pay attention to that. Yeah, because now we need to make a specification where
you have to make them not equal.
x minus A is not equal to R. Well, obviously, if this is true, then they're not equal, right? So we don't really need to specify that. I guess that we could go through the proof again to use handling each case. I wonder if I made a note about it in here. That's that. No, I didn't make a note about it in here. So, yeah, I don't really like that we're doing that. But the same way that we prove this, we could prove it with less than symbols. There's no reason that we had to have the inequalities in the proof there. So I think we could just reconstruct the proof the exact same way we did, except for only using less than, and we'd still be good.
But what happens when they are equal?
Well, if this is true, then they're not going to be equal. And if this is true, then they're not going to be equal.
So you're saying,
So you would show this implies this and this implies this.
right.
Do it without the equals, and it's already going to take care of that case for you.
Right.
Right? So, yeah, that's a good point. Now you're making me wonder if in the book they did have lessons, I just did lessons or equals.
Well, either way, it's basically.
It's going to be an identical proof, but yeah,
just
now
ignore there, right?
I've got to go look at my notes and the book. But either way, we're still good with that. This will be true with the same thinking, right? This is just using this theorem again, except for if we just had lessons instead of less than or equal. Are we good with going from here to here? Or is there anything we don't like? All right. Then we're going to add a to all three sides. So when we add a to negative r, we get a minus r. This last time when we add a to x minus a, we're going to get x. And when we add a to r, we're going to get a plus r. You good with that?
Mm-hmm.
So that's our second one here. So we said this can be rewritten this way. And then x between these two numbers, that's exactly what we mean when we say that x is in the interval a minus r, a plus r.
Okay.
When we say x is in that interval, we mean exactly this inequality.
Right.
Right? Pretty straightforward. Anything weird there?
Why is that useful?
This exact looking thing is exactly what we're going to be talking about when we talk about a limit. So,
So it's setting it up, basically?
yeah, you'll see us using it right as soon as we finish up with this side and move over there.
Did we define limit today?
Yeah, we will.
Oh, yeah, there it is.
So now let's prove some basic formulas that you are always useful. They're going to come up over and over again, so it's just good to know the formulas and we'll prove each of them. So the first one that we're going to prove that a to the n minus b to the n is equal to a minus b times a to the n minus 1 to b to the 0 plus a to the n minus 2 b to the 1 plus continuing like that until we get plus a to the 0 b to the n minus 1. So before we prove it, make sure we understand what this is saying. You understand what this pattern here is doing? Maybe let's write a concrete example real quick.
Well, it's very similar
It's
to
not
binomials.
0.
there.
A to the 0.
That's just 1. So you don't have to have it in there. Anything times 1 is just that thing. So notice that when I wrote it here, I didn't put the b to the 0, but just helps you see the pattern of what we're talking about. So as an example, if I was looking at 3 cubed minus 2 cubed, that's going to equal 3 minus 2 times 3 squared, 2 to the 0 is just 1, plus 3 times 2 to the 1, plus 3 to the 0 times 2 squared.
Why are your ends different over there?
They should be cubed both.
Oh, both of them should be cubed, sorry. Good catch. So this is what the formula is saying. Let's check that's true. What's 3 cubed?
27.
Minus 8 is
19.
19, so we got 19 here. 3 minus 1 is 1. 9 plus 6 plus 4 is 19. Yep, it worked. So there's an example of the formula in action. We don't usually use it for calculations like this. We usually use it for if you need to factor terms. Then
Oh yeah, that would be useful.
you can always factor. If you have a difference of anything to the same power, you can always factor out an a minus b. So let's prove it real quick. So we're just going to evaluate this side and show it's equal to this. Okay? You understand what I'm saying? So I'm not going to do a formal proof. We're just going to write out, we're going to evaluate this and see we get a to the n minus b to the n. So let's evaluate this. Distribute out my a. What do I get? A times a to the n is what?
A to the n.
Thanks to the end.
Yeah, a times a to the n minus 1, sorry, is a to the n. And b to the 0 is just 1. Plus, a times a to the n minus 2 is
A to the n minus 1.
a to the n minus 1. And then we have a b plus dot 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 plus, let's do my second to last term real quick. So let me put one more term up here. Let's do a to the 1, b to the n minus 2 plus a to the 0, b to the n minus 1. So let's do this term. A times a to the 1 is going to be a squared, b to the n minus 2 plus a when we multiply by this is going to be a b to the n minus 1. Oops, minus 2 here. Did I make any mistakes?
No.
So that's what happens when we distribute through our a. Now let's distribute through our negative b. Negative b times a to the n minus 1 b to the 0 is going to be negative a to the n minus 1 b to the 1 times b to the 0 is b to the 1, right? Negative b times this term, what do we get? Since we don't have it written up here, we'll skip that one. We'll go straight to this one. So minus dot dot dot
Wait,
minus. Huh?
what did you do?
I should have put one more term in there
Just why are you skipping it? I'm not.
because I thought you'd be able to see the pattern without it.
Well, I can see the pattern.
I'll squish it.
I'm just wondering. I was just wondering why you're doing it, but I see the pattern.
So all that they all line up. So this one was a to the n minus 1 b. We'll do the next term would be a to the n minus 2 b to the 2 dot plus or minus dot 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 minus, and then try and reline up right here.
Right.
So negative b times, shoot, we're missing the term there. Negative b times the term that comes right before this term,
Which we know what it is anyway.
yeah, is going to be a squared b to the n minus 2 minus negative b times this term is going to be a b to the n,
No.
a b to the n, oh sorry, this is by this term. Negative b times this term is going to be negative a b to the n minus 1, and then negative b times the last term is going to be negative b to the n. Okay. Did I miss something up?
No.
Okay. So then when you add them all up, you're going to get a to the n. That's going to cancel out with that. There would have been a term here that cancels out with that. That cancels out with that. That cancels out with that. All the way down, leaving just your minus b to the n.
Cool.
So all the other terms cancel out except for this times this and this times this. Everything else in between is going to end up canceling out. That's how you show it. Make sense?
Mhm.
Our next formula, geometric sum. So that is at 1 plus r squared plus dot 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 plus r to the n is equal to r to the n plus 1 minus 1 all over r minus 1. Here's the next formula we're going to prove. You understand what the formula is trying to say? Where r is some number not equal to 1. Because r equal to 1 obviously gives us problems in the denominator. Good? So let's prove it real quick. Well, using this formula, what do I know? I know that r to the n plus 1 minus 1 to the n plus 1 is equal to r minus 1 times r to the n plus r to the n minus 1 times 1 to the 1 plus r to the n minus 2 times 1 squared plus dot 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 plus r to the 1 times 1 to the n minus 1 plus 1 to the n. You good with how this is just using this formula? This formula right here? We're plugging in r for a and 1 for b.
Huh. Okay. And n plus 1 for n, right?
And n plus 1 for n, yeah. Probably should have wrote it a little bit different. Should we fix that real quick?
No, it's fine.
You want to leave it? Okay. Anyways, so we have that this is equal to this. Obviously, minus 1 to the n plus 1 is just minus 1, right?
Yeah.
Now, what are we going to do? We're going to divide both sides by r minus 1. So then I get r to the n plus 1 minus 1 over r minus 1. When I divide this side by r minus 1, I'm just left with this series. R to the n plus r to the n minus 1 plus r to the n minus 2 plus dot 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 plus r plus 1. Or if I write the series in the other order, it's going to be 1 plus r squared plus dot 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 plus r to the n. which is our formula. Good?
This is where n is a natural number, right?
Yeah, for n being any natural number. Any natural number, yeah.
Does it work when n is 0?
0 is not a natural number in this class.
I know, but no, right? No.
No, it doesn't. Because then you have r minus 1 over r minus 1. Well, that just gives us 1. So, yeah, actually it does work. It tells us that 1 is equal to 1 over 1. So.
Oh.
Okay. So that covers those formulas. Now we have another definition. Now the author makes a messy definition for defining factorial because he's trying to show you that it's defined for all natural numbers. So I'm going to give you a simple definition and then go over his definition. So in defining factorial, here's what I say. Define 0 factorial equal to 1, comma. Then, for all n in n factorial is equal to n times n minus 1 factorial.
Right.
We've all come across factorials before?
And for the natural numbers in this class, you could start at 1.
Yeah, the natural numbers in this class start at 1.
So you don't even.
No, we need 0 factorial because when I plug in 1 factorial, what is 1 factorial? 1 factorial is equal to 1 times 0 factorial by this definition. What is 0 factorial? That's not a natural number, so I can't use this side. I have to use this side. Oh, 0 factorial, that's equal to 1. So that's 1 times 1, so 1 factorial is 1.
Okay. Yeah.
Right? But then for a bigger number, what's 5 factorial equal to? Well, that's equal to 5 times 5 minus 1 factorial, or 4 factorial. And then we continue until we got 5 times 4 times 3 times 2 times 1 times 0 factorial, which then 0 factorial is just 1.
Your factorial should be inside the parentheses, right?
Oh, doesn't matter.
Doesn't it?
It does.
No, factorial happens before multiplication, so.
Really? What's its order in the order of operations?
I'm not sure where it goes compared to exponents, but it's on par with exponents. Anyways, I think we all understand factorial. Quick question, what's 3 factorial?
3 times 2 times 1.
Which is?
6.
6. Okay, now let's go over to the author's convoluted definition. The reason he gives it the way he does, he's given it kind of like the same way we think about proving something's inductive. That way he's showing us works for every natural number. So let n be a natural number. Then we define 1 factorial to be 1. And if k factorial is defined, then we define k plus 1 factorial to be k plus 1 times k factorial. Thereby defining it for all n and n. And then we also throw on 0 factorial equals 1 since that wasn't covered by the definition. It's a logically equivalent definition. Why is he showing it this way? He says, look, we have it defined for 1, and if we have it defined for k, and if we have it defined for k, then we have it defined for k plus 1. Therefore, it's defined for all natural numbers. Therefore, we can always take the
That's not the worst definition for it.
It's not
factorial.
that bad.
No, it's not that bad. It's just, this is a lot cleaner.
It's pretty much the same thing.
It's the exact same thing. They're defined identical ways. It's just, he went through a lot of effort to make sure that you understood. We can now take the factorial of any natural number. If you like that definition, you like that definition, that's fine. It's good to like it. So that's factorial. Now we have this other notation that you guys from discrete math are going to be very familiar with. N choose k. Now, n choose k in discrete math, we had a definition for what that actually was.
That is not
And we
bad.
proved that it happened to also equal n factorial over n minus k factorial times k factorial.
You just defines it like that?
He just flat out defines it like this.
Oh, why?
Because our definition was a counting definition.
Mm-hmm.
We're not going to get into counting in this class. And so we're just gonna let this be the definition, since we have this defined. There's no problem doing it this way. I mean, you could define it this way and show, oh, and this also happens to count all k element subsets of an n element set.
That's how I think
We
about
just
it.
defined it the other way, and there's gonna be context we're thinking about that way. Helps you prove things a lot easier than thinking about this way.
What is thinking about this way say?
That it's just that.
Oh.
I mean, there's no high level intuition for how to think about it. It's just that formula. This is shorthand for that formula. I mean, similarly, we didn't define factorial this way in discrete math. We defined factorial in terms of combinations again.
Did we?
Yep.
Will you just give an example of that really fast? Just to like.
Yeah, so let's say we want to know what 3 choose 2 is. So that's going to be 3 factorial over 3 minus 2 is 1 factorial times 2 factorial, which is equal to 6 over 2, which is equal to 3. So that's using the formula. The way that we set it is if you have a 3 element set, then there's going to be 3 2 element subsets you can create from it. So if I have A, B, C, how many possible subsets can I get from that set with 2 elements? 3. I can do A and B, I can do B and C, or I can do A and C. So 3, same thing. Good? Okay. Notation. I think we already understand the summation notation. Should we, let's just do one convoluted example to make sure that we know exactly how to use it. Let's say I'm doing the sum from 4 to 7 of, from k equals 4 to 7 of k squared minus 1. What is this equal to? This is equal to 4 squared minus 1 plus 5 squared minus 1 plus 6 squared minus 1 plus 7 squared minus 1. Here's where we start plugging into that formula. Here's where we end. So we plug 4 in, and we add it to what we get when we plug 5 in, and we add it to what we get when we plug 6 in, etc., all the way to 7. We stop when we reach 7, whatever's at the top. Three. That's supposed to be an n there. Sorry. So if we're doing the sum of just k from 1 to n, what is that? That's 1 plus 2 plus 3 all the way up to n, wherever we stop. Good? Okay, next, Pascal's identity. This is also something that we proved in discrete math, I think, or it was a homework problem.
Yeah, we did.
But we'll prove it real quick. What are we proving? We're proving that n choose k, a fraction, sorry. N choose k is equal to n minus 1 choose k minus 1 plus n minus 1 choose k.
Where is this in a book?
Pascal's identity should be close to the very end of the section. They just throw all these formulas right at the end. So it should be right over binomial theorem. Does he not get it? Scroll down. Oh, what the?
I think that's what you just talked about. And
Yeah.
it goes right to this.
Scroll down some more. I don't know.
Did you just throw this in there?
I'm sure I had a reason for putting it in my notes before. I mean, you use it for proving the binomial theorem,
Maybe that's fine.
so that could be why. But I didn't intend to prove the binomial theorem because that takes too much time for what you get out of it. So we'll go over this. This will get you comfortable with using this notation. And then, yeah, we'll just prove it. Okay, so let's prove that these things are equal. So I'm going to evaluate this expression and show that it's equal to this expression is the way I'm going to do it. Okay? So let's evaluate this expression. What is that? That's n minus 1 factorial over
N minus 1.
n minus 1
So really n minus k minus 2?
No, that's, let me make sure I got plenty of space to write this, let you see it. N minus 1 minus k minus 1 factorial times k minus 1 factorial.
Isn't that n minus k minus 2?
No, because the negative is going to make that positive, and it's going to turn out to be just n minus k.
Oh.
So this is just writing this out, right? The top factorial divided by the top minus the bottom factorial times the bottom factorial. That's this one. Plus, write this one out. N minus 1 factorial over n minus 1 minus k factorial times k factorial. We good with that so far? Okay. So, I'm going to simplify this expression. Notice that this is just n minus k factorial, is what this is, right? So I'm going to rewrite this as n minus k factorial, and at the same time I'm going to multiply this expression top and bottom by k. So, stick with me.
Hey, wait a minute. How did you get k for k minus 1 in both of those? N minus 1 minus k minus 1.
That's the bottom.
Over there is just k. Oh.
This is this one.
Okay,
Okay. So, simplifying here, I'm going to multiply top and bottom by k, and simplify this inner expression at the same time. So we have k times n minus 1 factorial, all over, this is now just n minus k factorial, and then k times k minus 1 factorial is just k factorial.
Why are you times it by k?
I multiplied this one top and bottom by k.
Okay.
So far we left this expression alone.
Wait, how do we know that k times, oh wait. Yeah, how do we know that k times k minus 1 factorial is k factorial?
What is k factorial equal to? It's equal to k times k minus 1 factorial.
Oh, right. Okay, never mind.
Or in other words, 5 factorial is equal to 5 times 4 factorial, to put concrete numbers in. So are we good with what I did to this one? And then over here, I'm going to multiply this top and bottom. I forgot to plug in a charger to that phone.
It is at 20%.
Good thing you gave it an awkward eye.
Well, I'll let you know as soon as this is done, but figured I'd just wait until you're done with the proof.
Set it up before class.
So why don't you just do discrete math in here?
Physics
Oh,
needs this room because it has all the physics equipment.
that's right.
And the reason that I don't just do this downstairs is we're already in this room on
Right.
Monday night, so it lets me fill out the whiteboard. I hope it's charging.
Is it plugged in all the way?
Yeah, but there's no feedback to me that it's working. Well, that does. We'll know if it dies at least, and then we can figure it out then. Okay, anyways. So now for this expression, I'm going to multiply it top and bottom by n minus k. And then multiply this top and bottom by n minus k.
You're just trying to get common denominators?
Yeah, that's it. I'm just getting common denominator. Same way you add fractions all the time. So we're going to get n minus k, n minus k, times n minus 1 factorial, all over me just write it, maybe you can see it.
Yeah.
N minus k factorial times k factorial. So I times this top and bottom by n minus k, the n minus k in the top's there, but n minus k minus 1 factorial times n minus k is just n minus k factorial. You good with that?
N minus k times
Yeah, let's write it.
k factorial.
N minus k factorial is equal to n minus k,
No, I know that part.
n minus k minus 1 factorial. So when I take this, and then multiply by n minus k, I get this. Oh,
I got that part. I'm wondering about the k factorial.
oh, that's just right there.
Don't you have to times n minus k to it?
You did?
If I have 5 times 3, and I want to multiply it by 2, then that's just going to be 10 times 3. It's not 10 times 6. The 2 only goes one term. So my n minus k only needs to go to this term. Doesn't need to do it to both. 5 times 3 is 15, times 2 is
You
30.
did it to both terms on that side.
No, this term stayed the same. I was just rewriting this. This is n minus 1 minus 1 is going to make it plus 1 minus k.
Oh, right.
So this is just rewriting this identically.
So you just choose which one you want to times to?
Yeah,
This is so dumb. Okay.
because 5 times 3, when we multiply that by 2, it could be 10 times 3, or it could be 5 times 6. Both of those are perfectly valid ways of multiplying by 2, right? So now, we're right here in the expression. So we've got a common denominator now, so I can put them all over the same denominator. And I'm going to factor an n minus 1 factorial out of the numerator. So factoring in n minus 1 factorial out of the numerator leaves me with a k plus n minus k. And then our denominator now is just n minus k factorial times k factorial. Now, k plus n minus k is going to be just n, and n minus 1 factorial is just
And factorial.
n factorial. Perfect. So this is just n factorial all over n minus k factorial times k factorial. Which is what this is equal to n times k. Why do I keep doing that? Okay. Good? Alright, then the binomial theorem. We're not going to do this one, but we're going to make sure you at least understand it. And we'll write it out for a term. So, here's the binomial theorem. A plus b to the n is equal to this sum. Let's put in actual numbers to see it expanded out. We can keep a and b variables, but let's pick an n. Give me an n.
2. Probably bigger one. 4.
A plus b to the 4. So what's binomial theorem saying? It's saying that this is equal to, first plug in 0. So it's saying it's equal to 4 choose 0, because remember, we just picked an n. We picked our n to be 4, we're going to write this out for n equal to 4. Okay? So, we're going to do the sum of this, plugging in 0 for k, then 1 for k, then 2 for k, then 3 for k, then 4 for k. So we're going from k equals 0 to 4. We're writing out this formula for the case when n is 4. So it's equal to 4 choose 0 times a to the 4 minus 0 times b to the 0. There's our first term. Plus, our next term is going to be, now we're plugging in 1 for k. So it's going to be 4 choose 1 times a to the 4 minus 1 is 3, b to the 1, plus, now we're plugging in 2 for k. 4 choose 2 times a squared, b squared, plus, now we're plugging in 3 for k. 3 choose, 4 choose 3. 4 choose 3 times a to the 3, b to the 1, plus 4 choose 4. I start counting a's up again. Oops.
Yeah.
A, 1b cubed, and then finally b to the 4th. So that's plugging it in for this formula. Right? And you could just evaluate this real quickly now. 4 to 0 is going to be 1, a to the 4 plus 4a cubed b to the 1 plus,
That's 6.
let's see what this one is. So 4 choose 2, what is that? That's going to be 4 factorial over 4 minus 2, which is 2 factorial, over 2 factorial. So we're going to get 24 divided by 4 is 6. So 6a squared b squared plus 4 choose 3 is just going to be 4ab cubed plus 4 choose 4 is just going to be 1b to the 4. If you're not comfortable evaluating these real quickly, you'll get there.
Yeah, you will be. But you didn't.
Yeah, once we cover these in discrete math, you'll be very used to calculating these. So for example, how do I know that 4 to 0 is 1 right out the door without even thinking about the formula? How many 0 element subsets can I make from a 4 element set? 1, the empty set. That's the only subset of a 4 element set that has no elements in it. Same thing with 4 choose 4. How many sets with 4 elements can I create from a 4 element set? 1, the set itself. So some of these, sometimes when you're evaluating these, you think about it in terms of sets rather than the formula. And then if you don't want to think about
It's
the
really a
sets, you
lot
can think
easier.
about the formula.
For the smaller numbers, it's a lot easier.
Yeah, sometimes it's easier to think about one way, sometimes it's easier another way. So that's the binomial theorem. That's the formula for expanding it out. You just need to know how to expand it out and then be able to plug those things into the formula and you'll be fine. But as you work with these more, you'll just get used to it. It won't be such a big deal. Okay, so that ends the 1.3 material. So now we're ready to do the 1.4 material. So try to move the camera now.
1.4.
Or sorry, 2.1. So there's 3 major ideas in calculus, not 3, 4. There's 4 major ideas in calculus, 4 major definitions, and those are that of a limit. I'm going to need to put it right here.
You know, why
I guess I could probably put it behind.
aren't you going to be teaching us section 2 next week?
Chapter 2? We're going to start it this week. Oh, you weren't here when we had that conversation, were you?
I don't know, but why?
About the tests?
I was, like, the test is for homework tonight, so we're not gonna be doing 2. So you might.
You can start on 2 if you want, but it's not going to be due next week.
Right, that's my whole point. You're gonna be teaching us 2 next week.
We're going to
So
start it right
why
now
start it right now?
as a cushion. So that we don't have to worry about getting behind later. Ew.
Does that work?
Yeah, we're fine. Zoom out a little. Okay. So there's 4 major ideas in calculus that you cover. The first major idea is the idea of a limit or convergence, which we're going to cover today. The next idea is the idea of continuity, and then there's differentiation and there's integration. And you've probably heard about all those things before without knowing really what they are. But showing that something is continuous, or defining a derivative, or defining an integral are all special cases of limits. So they're all types of limits. So we need to understand what a limit is. The stuff for 2.1 is probably the most basic stuff for all the rest of calculus. The idea of the limit. You need to understand what a limit is. So if anything doesn't make sense, you've got to stop me. We've got to make sure we understand it. And since we are now going to be getting a little ahead, it's okay if we go through this stuff really slow and make sure it all makes sense. So let's get going. So the first definition is going to be that of a sequence. A sequence of numbers is a real valued function. What does it mean for a function to be real valued? It means that the image is real numbers. It spits out real numbers. So a sequence of numbers is a real valued function whose domain is all the natural numbers. So it maps every natural number to a number, in other words. So it's a function of the form n to r. Domain's every natural number, and then what it spits out is just a real number. So before we get a high level example, let me just scribble one out really quick. So low level, when we're looking at the sets it's actually composed of, it's going to take 1 and map it to some real number. It's going to take, we'll call this A1. It's going to take 2 and map it to some real number, we'll call it A2. It's going to take 3 and map it to some real number, we'll call it A3, etc., etc. It's going to map n to a sub n, etc., etc. Goes on forever. There's an infinite number of things in there. It maps every natural number to some real number. If it's a function of that sort, it's called a sequence. Feel like we're good so far?
Mm-hmm. We've dealt with sequences before.
Yeah, you can basically think about the way we do lists as sequences if you want. Kind of.
Well, kind of.
Yeah, kind of. Alright, so notation. You're used to when we are representing a function on the real numbers, we write something like f of x is equal to something, maybe y, I don't know. F of x is equal to y. The notation that we're going to use is the nth term, we're going to use a sub n to represent that thing, exactly how I wrote it here. The nth term, the number that's paired with it, we signify with a sub n. So a sub n is our standard notation for the thing paired with the nth term, the same way that y is our standard notation when we're talking about real numbers for the number paired with x. Understand what I'm saying? Just standard convention. Now, this is where it gets kind of weird. We say f of n is equal to an, or we write an in scribbly brackets like this. This is not talking about just a set of numbers. Since we're only interested in their right-hand things, since we're only interested in the a1, a2, a3, a4, a5, so sometimes we, instead of writing it this way, let me keep scribbling here. Instead of writing 1, a1, 2, a2, 3, a3, sometimes we just instead write a1, a2, a3, an, and we keep writing like that. And our shorthand for this is just an.
Oh.
So that set containing an is a set of numbers, but you just
But the order matters. So when I list these out, a1, a2, a3, a4, etc., this is first, this is second,
So
this is third.
it's not really a set, it's a list.
So yeah, this is it's a sequence of numbers. Order matters. So this is the first number, this is the second number, this is the third number, etc.
Then why don't you put it in parentheses and not
Yeah.
curly brackets?
Because it's not technically a list either. So it's like pick your poison. You got to pick a notation to use. This is a standard notation that's used. So the same way that I might signify a function really quick by saying you get the right-hand thing by squaring the left-hand thing, f of x is equal to x squared. We also use that kind of notation for telling us how we get the nth term in our sequence. So what's paired with 1? Whatever you plug in, whatever you get when you plug in 1 for n. What's paired with 2? Whatever you get when you plug in 2. What's paired with 3? Whatever you get when you plug in 3. So when I write 1 over n like this is a shorthand for 1, comma 1/2, comma 1/3, 1/4, which you know that this is obviously shorthand for 1 is paired with 1, 2 is paired with 1/2, right? So this is what the function actually is. Since we only care about the right-hand things, we write it this way. And then since there's a standard way of figuring out what the right-hand thing is from the left-hand thing, then we write it that way, whatever that pattern is. The nth term is just 1 over n in this case.
I see.
Is that making sense?
Yeah.
So just to connect this example to what you're showing over here, 1 over n is the a sub n, and then
Yep.
your list of fractions is the list of a1, a2.
A1, A2, A3, etc. We can continue this, comma, 1 over n, comma, and it goes on forever. This tells you how to get the nth term. Alright, so let's expand this one out to make sure we got it. So what's the first term in this sequence going to be?
-1, or sorry,
Just 0.
0.
0, right? When I plug in 1 for n, -1 to the 1 is -1. 1 plus -1, 0. Okay, what's the second term?
1.
2.
No.
2.
2.
-1 squared
Right.
is 1. 1 plus 1 is 2.
And they're just going to alternate, right?
What's the third term?
0.
0.
Then 2.
Because -1 cubed is -1 times -1 times -1 is -1. 1 plus -1 is 0. And it's going to alternate. 2, 0, 2, etc. Okay? Feel like we're getting comfortable with sequences? See some more examples or move on?
We're good. Oh, wait, I'm just typing it. Okay.
More examples?
Fine.
Fine. That doesn't sound like very fine. Let's do one more example. Let's look at the sequence n plus 1 over n. There's a common one. What's the first term in the sequence? My brackets are being atrocious. Huh?
2.
2. Or 2 over 1 if we want to keep the fractions in there. What's the next term? Plug in 2 for n.
3 halves.
Yeah. 2 plus 1 is 3 over 2 is 3 halves. What's the third term?
Oh, it's going to be 2.
No.
I mean, not 2. Whoops.
4 thirds.
4 thirds. What am I doing? That's 5 fourths.
And then 5 fourths. And then when you plug in 5, you get 6 fifths, etc.
Right.
Good?
Yeah.
Probably because we did that example.
I don't know why I said that.
Okay. Rather than defining sequence this way, we might also define it recursively, kind of like we define factorial recursively. So I could say, let the first term be 1, then to get the next term, here's what you do. If the previous term squared is less than or equal to 2, then take that term and add 1 over n to it. If the previous term squared is greater than 2, take the previous term and minus 1 over n from it. So here's a more convoluted example. Let's write it out and see what we get. So what's the first term?
1.
Yeah, that's the easy one. 1's the first term. Now, what's the second term? Here's what we do. We look at the previous term, 1.
3
Is
halves.
1 squared less than or equal to 2?
Yeah.
Yeah. So we're going to use this one. So it's going to be 1 plus 1 half, or 3 halves. Right? Now let's find the next term. The next term, how do we find it? We look at the previous term,
Wait a
square
minute.
it.
You have 2, right? 2 squared is not less than or equal to 2.
This is 3 halves.
Yeah, but it's the second. But
So the previous term squared.
oh, right.
Yeah.
There we go.
So the previous term squared, what is that?
It's 9/4.
9/4. Is 9/4 less than or equal to 2? No. Because 8/4 is 2, so 9/4
It's not.
is going to be more than 2. So since 9/4, or the previous term, 3 halves squared, is bigger than 2, we use this pattern.
Right.
So we do 3 halves minus 1/3. And what? Huh?
Never mind.
So what's 3 halves minus 1/3? 9 6 minus 2 6 is 7 6. Did I do that right?
Probably.
Well, check it. Don't just say probably. 3 halves minus 1/3. What is that?
It's 6. No. Yeah, 9 6 minus 2 6.
Which is 7 6. Okay, let's figure out the next term. We need to figure out which of these we're going to use. How do we determine that? We look at the previous term squared, and we see if it's less than or equal to 2 or greater than 2. So is 7 6 squared greater than 2?
No,
No. 49 over 36
it's less than 2.
is going to be less than 2. We'd have to be all the way up to 72 over 36. We only have 49 over 36. So it's less than 2, so we're going to use this one. So we're looking at 7 6 plus 1/4, right? Am I saying that right?
Yes.
So what's 7 6 plus 1/4? Now let's see, that's going to be...
49 plus,
What are you doing?
well, I'm,
That's going to be 28 over 24 plus 6 over 24,
okay.
right?
I was multiplying by 6 for some reason. My needs to do 4.
Is 6 not the common denominator? Or 24, I mean?
No, 24 is, you're right.
So what do we have? We have 28 over 24 plus 1/4 or 6 over 24, which is going to give us 34 over 24, which is the same thing as 17
No, wait.
twelfths.
We're adding 1/4 to it?
17 twelfths.
Yes. Okay, so let's rewrite out what we
I
have.
feel like 12 could be, right? Isn't that the common denominator?
No.
Yeah, we could have used 12.
Either way, it's the same.
Times 2 and times 3. Yeah, good call. That's why it could reduce. So timesing by 2, we get 14 over 12 plus, and then what's 1/4 in terms of twelfths?
3/12.
3 twelfths. So that's the same thing as 17 twelfths. Good call. And then, once again, we can continue. Is 17 twelfths, when you square it, is it greater than 2?
Ooh.
I don't know either.
I don't think so. I don't think so.
I would bet that it is.
Okay.
Just because 15 squared is already 225, and we only gotta get to what, 288? So, I would bet that is, but... Oh well, you know how to continue the pattern. It takes a little bit of computing. Obviously, if you have a calculator, it'd be pretty
What is
easy to do.
What is
By
it?
the way, calculators 1% allowed here. So feel free to use whatever calculator you want for anything we're doing.
What does a graph of that look like?
What does the graph of this look like?
Yeah.
So what the graph of this is going to look like is, here's 0,
Right.
here's 1, here's 2, square root of 2 is going to be somewhere around here, here's square root of 2. And so it's going to be looking like
Oh.
narrowing in on the square root of 2.
That makes sense.
So, something like that. That's my guess. Your guess is as good as mine. That's what it feels like it's going to do. Okay,
Are we going to be covering all of this next week?
we can recover anything you want to cover next week.
Right, but next week's homework is this.
Yeah.
So why don't we just cover this next week? And
So that we have
stay
a
on
cushion.
chapter 1 when we're going to be doing the test this week.
Because we have an hour and a half.
Okay, but we could go over chapter 1.
We already did.
I'm saying we could do a review.
We're just going to set up
This doesn't give us a cushion at all, if you think about it.
Why?
Because it's not like we're going to be doing 2.1's homework.
if we need to restart 2.1, that's perfectly fine. Then you get to go over limits twice.
So why not just stay on chapter 1 this week?
Because then we would have done the test right now.
Why
So,
don't we do the test right
we already made the choice.
No.
Alright,
It's just hard because it's like, it's so freaking much information.
it is.
Okay,
And so we can go over it again. It's barely you get
right, but
introduced
why
to
don't
it
we
twice.
just stay on chapter
as
1
opposed to
since
one.
we haven't even done the test yet?
There's nothing
To-
uncovered.
Build a cushion, yeah, we have nothing else to do. We could just sit and talk about chapter 1 all day.
Yeah.
Did you have questions for chapter 1?
If I did, would we go over it?
We sure would.
Okay, sure, I have some questions.
Bring up your question.
Well, actually, I didn't have any questions, but,
Okay,
hang on, I still disagree with what you're doing. So can
that's
we-
fine.
Can
You
we
can
talk
disagree.
about it?
What would you like to talk about?
Because I feel like doing this is not productive.
Okay, that's how this material is going to
It's
feel.
called brain overload.
I understand. So we're going to overload your brain, and then we'll re-go over the material. If that's what we need to do.
Why do that though?
Because exposure twice is better than exposure once. It's better to overload your brain, stretch your brain, and then go back and try to do it again. It's a common strategy, for example, when it comes to reading a dense book, is to force yourself to read all the way through the material, even though the material isn't making sense.
This
And
is
then
making
go back.
sense. It's just you're teaching us so much in one day, and it's like we're not even going to be doing the homework for this.
Well, we'll go over, as soon as we finish this, we're done talking about new material, and then we're just doing a bunch of examples to see it in action. Okay, so moving on. Definition now of a sequence. Oh, sorry, of a series. So a sequence is just an ordered collection of real numbers, basically, right? That's what we were building here. We were building a sequence, a sequence, a sequence. If you have a sequence, then we have the notion of a series on the sequence. How do we create a series from a sequence? We add up all the terms to the term in this. Well, better to see an example and then explain what this is saying.
Well, I mean, that's one of the things. We've done them in algebra. Maybe it's because I took algebra last year, but
Yeah, you did these in college algebra, but
we did so many.
yeah, so you've had a lot of practice with them, but these guys haven't. So let's look at the series or the sequence, and 1 over 2n is a good one to look at. So 1 over 2n, what's this equal to? First term,
1/2.
1/2. Next term,
1/4.
1/4. Next term, 1.
6. Right?
That's not how I meant for it to go. What did I do wrong?
1 over 2 to the n. Maybe that's what you're doing.
Oh, I meant to do 1 over n squared.
Oh.
Let's restart. Okay, first term.
1.
Second term. Oh, it's still not what I'm after. 1 over 2 to the n.
That's what I said.
Oh, that is what you said? Sorry. There's what I'm after. Okay, because this is going to bring us up to Zeno's paradox. So first term is going to be 1/2, second term 1/4, third term 1/8,
60.
fourth term 1/16, etc., etc., etc. So Zeno's paradox was, he set up a scenario. He says, imagine that Achilles, some great athlete, is racing a tortoise. And the way that the race is going to go is that Achilles starts here, but the tortoise gets to start at the halfway point. Right? So the question was, well, actually this isn't exactly Zeno's paradox, but it's a similar case. So I'll explain Zeno's paradox, and then we'll talk about this sequence. So Zeno says it's impossible for Achilles to ever pass up the tortoise, because by the time Achilles gets to where the tortoise was, the tortoise, however slow it's going, still went some distance. Well, by the time it takes Achilles to get to where the tortoise is at that point, the tortoise is still going to have gone further still. And that's going to go infinite, 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 infinite. You can do that an infinite number of times, and so Achilles is never going to catch up to the tortoise. So Achilles can't beat the tortoise in the race.
Doesn't make sense.
Well, it kind of makes sense, but it's obviously not real.
Well, yeah, so one of the arguments he was making is that motion in the universe is an illusion. We'd have to get way more to the
What value?
philosophy to...
What value does that have?
Well, that's a very relative term.
Like, yeah, he considered that situation, but that doesn't actually have any relevance.
Well, this is a real question though. How is it possible that Achilles passes up the tortoise if he has to cover an infinite distance?
But he doesn't.
He has to cover the sum of infinite distances. Isn't the sum of an infinite set of distances an infinite number?
No?
No. How can you prove that?
How can you prove
By
it?
taking the limit.
So you need to do something like take a limit, which is something very sophisticated. And it took us a long time to come up with the idea of a limit.
Oh, so the Greeks were like, oh,
So this is ancient Greeks trying to solve the problem. We have a way of handling this type of notion today. So what we're going to show eventually at some point is that 1 plus a half plus a fourth plus an eighth plus a 16th plus a 32nd, and if you do that to infinity, the sum is actually 2. It's equal to 2. Not really close to, not approximating. It is 2. Anyways, so here's a sequence. Now we're going to create a series from the sequence. How do we create a series from the sequence? So my series then is going to be the sequence we get when I sum up. So if this is a sub n, I'll just plug it in all the way, actually. From k equals 1 to whatever term we're looking for, of whatever our sequence is.
And that would be S sub n.
2 to the n. Yeah. So if this is Cn, here's Cn. Then this right here is Sn. Where Sn is going to equal the sum from k equals 1 to n of C sub k. So that's a lot of notation. So let's see it as we expand it out, and then that will help the definition make sense. So the first one, we're going to add up from k equals 1 to 1 of 1/2. So that's just going to be 1/2. With me? The second term, we're going to add up from k equals 1 to 2 of 1 over 2 to the n. That's going to be 1/2 plus 1/4. Make sense? And then for the third term, we're going to add up from k equals 1 to 3 of 2 to the n. So we're going to do 1 over 2 to the 1 plus 1 over 2 to the 2 plus 1 over 2 to the 3, which is going to be 1/2 plus 1/4 plus 1/8, etc. You continue this way. So that's how you get a series from a sequence. So if Cn is a sequence, let's just say it exactly, let Cn be some sequence, and define S of n by the nth term in S of n in this sequence is equal to this partial sum of this sequence. So a series is just a sequence. Notice that this is still just a sequence. I took this sequence, I'm constructing a new sequence from it.
So you can create a series on a series.
Yeah, we could have used a series to construct a series. A series is just a sequence constructed from a sequence in this special way.
Is there kind of a pattern or a tendency that happens to the numbers when you do that? So what I mean is, for example, you were saying the sum of all of those distances would be 2, right?
Right?
If you were to take the series on that, what would happen?
That's going to be completely dependent on how the series goes, I think. I don't know, I'd have to think about, play with examples. Anyways, let's wrap our head around what this is in. So let Cn be some sequence. Then we're going to construct a new sequence, S of n, by, how do we get the nth term in S of n? We take the sum of the first n terms in C, in this sequence. Take the sum of the first n terms in this sequence, and that's what the nth term in this sequence is going to be. So then, then the sequence Sn is an infinite series, and the nth term of Sn is, we call the nth partial sum.
Right.
So this is the 1th partial sum, the 2nd partial sum, the 3rd partial sum, etc., etc. Till we get to the nth partial sum. This is what the nth term would look like, right? That's how we signify this. We show what the nth term would be. So that's what a series is.
The nth partial sum of that sequence.
Yes, of this sequence would be this. This is the nth partial sum of this sequence. The nth term in this sequence is the nth partial sum of this sequence. This sequence is a series on this sequence. Good?
Mm-hmm.
Okay, so that's a sequence, that's a series. So the next definition that we're going to have for this chapter is, or for this section, is the big definition for this chapter in general. Oh, I was going to do an example up there. I think I already wrote it right here.
It's that example.
It's the same exact example. Except for I wrote it wrong right there. That's supposed to be n squared. N squared. Okay.
No. Let's do
2 to the n. Oh my goodness. Okay. So definition now. Definition of convergence. This is going to be the exact same thing as the definition of a limit. And this is the whole heart of all of chapter 2. If you wrap your head around this, chapter 2 is going to be pretty easy from there on out. So, a sequence, an, is said to converge to a, that's a number, not a word, converge to a, provided that for every positive number epsilon you can think of, there is an index n such that the distance between a to the n and a is less than epsilon from that sequence onwards. So this is a very dense definition, so let's go over it a few different ways. Let's see what we're saying.
It's kind of like saying epsilon is almost like an upper bound.
Not quite. Epsilon's a distance. What we're saying is, pick any sequence you want. Let's think about a sequence that we know converges. What does it mean for a sequence to converge? Let's talk very high level what it means for a sequence to converge. A sequence converges if it keeps on getting closer and closer and closer and closer to a particular number.
Right.
So, for example, the sequence 1 over n, does this converge? Yes. What does it converge to?
0.
0. This keeps getting closer and closer and closer to 0. What our definition of convergence is basically saying is that a sequence gets arbitrarily close to a particular number. If a sequence gets arbitrarily close or really, really close to a particular number, it converges to that number. In our definition, we're calling that number a. So in this case, we say it's going to be 0. What about in this case?
No.
It doesn't. It doesn't get closer and closer to something, so it doesn't converge to that thing. So here's what our definition is saying. A sequence an is said to converge to some number a, get closer and closer to some number a, provided that for any positive number epsilon, for any really, really small number you can think of, I can find an index in the sequence such that from that index onwards, my sequence is always within that distance of epsilon. Let's draw a picture of
Wait a
it.
minute. Can we go over? Index n means the number corresponding to that index, or the index itself?
N is the index. A sub n, A sub big N is the term corresponding to that index. So here's what we're saying. So let's A1, A2, let me draw them closer together. A1, A2, A3, dot, 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 A sub big N, dot, 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 goes on forever. So,
Why do you use big N? Like, is that?
to reference our definition.
Oh.
So what we're saying is, so we've got some sequence here, and we can plot the point somewhere on the real number line. They might go back and forth. Who knows what they do? We're saying that if this converges to A, so here's A. If this sequence eventually converges to A, then for any epsilon you pick an epsilon, and let's draw out what epsilon marks around A. This would be A plus epsilon. Over here would be A minus epsilon. For any epsilon you pick, construct the interval around A, so that we're going epsilon to the right, epsilon to the left. For any distance you pick epsilon, then there comes a point plotting A, so A1 might be over here, A2 might be over here, A3 might happen to be in there, but A4 might be back out here. There comes a point in the sequence starting at A sub n, such that from that point onwards, we're always within epsilon of A. We're always in this interval.
Oh.
So A sub big N is in there, A sub big N plus 1's in there, A sub big N plus 2's in there, A sub big N plus 3's in there, all the way. All the infinite remaining terms are always in that interval. If I can show that's the case for any epsilon you pick,
And you get smaller and smaller and smaller.
yeah, you can get smaller and smaller and smaller. If I can show that that's the case for any epsilon you pick, I can always find an index in the sequence such that from that index onwards, we're always within epsilon of A. Then that sequence converges to A.
Can you define what the index of n is?
What this is,
Yeah, what index n is.
that's going to be the whole trick to proving something converges. So before we do this proof, because it's kind of a hard proof, let's do just a quick example proving that particular sequence converges to something so that you can get a feel for how this works, how you use the definition, and I think we'll do an example, then go over the definition again, and then if you still have questions, we'll attack them again. So let's do a proof that 1 over n converges to 0. Right? Like we know it should. Now, how am I going to prove this? Well, one, I need to get some random epsilon. Let epsilon in the positive real numbers. Let epsilon be any positive real number. I need to show that I can find an index big N such that this sequence from big N onwards is always within epsilon of 0.
And epsilon always has to be a positive number, right?
Yeah, epsilon has to be a positive number because it's a distance. A distance is always positive. If I have the absolute value of this is less than epsilon, epsilon has to be positive. Because absolute value can only be 0 or bigger.
And 0 is not a positive number.
No, it's not positive, it's not negative. So let epsilon, maybe keep track of where we're trying to get. Therefore, therefore the absolute value of 1 over n minus 0 is less than epsilon for all n greater than or equal to big N. So this is going to be what I'm trying to get to. If I show that this is the case, I'm done using this definition directly. If I can show that 1 over n minus what it's converging to, in this case 0, is less than epsilon for all n from this index onwards, then we will have proven it. So the whole trick is finding the index such that this line's true, and we're done. So let epsilon be an R2. By the Archimedean property, we know that there exists some big N in the natural numbers such that 1 over big N is less than epsilon.
Right.
Right.
This is why we use that so much in this class. I was wondering.
All right. 3. Observe that 1 over little n is less than or equal to 1 over big N for all n greater than or equal to n. In other words, if I make the denominator bigger, I make the number smaller. That's what this is doing. If little n is bigger than big N, then this number is smaller than this number. Make sense? Then, the absolute value of 1 over n minus 0 is equal to the absolute value of 1 minus n is equal to 1 over n is less than or equal to 1 over n is less than epsilon for all n greater than or equal to big N. Is less than epsilon for all n greater than or equal to big N.
How do you know that the absolute value of 1 over n is 1 over n and not 1 over negative n?
Okay. N is
It's a natural number.
it's a natural number.
Okay.
So its multiplicative inverse, so n's positive, so its multiplicative inverse is positive. This is its multiplicative inverse. Therefore, the absolute value of it is positive.
Okay.
Any other questions?
Don't you have to define capital N in terms, or well, don't you just have to like find what it is? Because you didn't actually say that capital N was equal to something.
Right. How did I get capital N? It's whatever the number is, such that 1 over it is less than epsilon. I'm guaranteed that there is such a natural number by the Archimedean property. There's infinite of them, but there's at least one, so grab one of them, and we'll call it big N. What number is it exactly? Who knows? We just know it satisfies this property.
Okay.
So from that point in the sequence onwards, whatever this sequence is, 1 over n. So I know that 1 over n is less than epsilon, so 1 over big N plus 1 is, 1 over big N plus 2 is, dot, 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 goes on forever, right? Doing this backwards is kind of weird. 1 over 2, our first term was 1 over 1, there it is. So we have 1 over 1, 1 over 2, 1 over 3, eventually we get to this 1 over big N, and we know that from this point onwards, the number is less than epsilon, or in other words, from this point onwards, the number is within epsilon of 0, the thing it converges to. Make sense?
Yeah.
Let's do another example. So we did that. Let's do this proof real quick. So let's prove. Sorry, we haven't defined this limit notation, so forget that for a second. I forgot to put it up here. It's going to be the same thing. We have to do this proof first, but anyways, we're going to prove that this sequence converges to 3 is what we're going to prove. Understand what I'm saying? Prove that 2 over n squared plus 4 over n plus 3 converges to the number 3. Good? So I'll begin it the exact same way. Let epsilon be any positive real number. And when will I have known I've proved this? I know that I will have proved it when I have shown that, therefore, the absolute value of 2 over n squared plus 4 over n plus 3 minus the thing it converges to, 3, is less than epsilon for all n greater than or equal to some index. So if I can find an index big N such that this is true from that index onwards, then we will have shown that it converges. You understand the big picture of what we're trying to get? Good? Okay. Now, here's where we got to do some dirty work. Oftentimes when people are doing these proofs, they kind of throw something out of the blue. I can show you what will be right out of the blue, and then you'll be like, how the heck did you get that? I'd say, by Archimedean property, there exists n in the natural numbers such that 1 over n is less than epsilon over 6. And that's where you're like, what the heck, where'd you get that? So, in proofs like this, we often do a bunch of scratch work in the background, and then we come along and do this and prove it formally. So let's do our scratch work on how on earth I knew that, right? So I know that the way to do it is to write this as, take the absolute value of I want this less than epsilon. Take this absolute value and keep manipulating it so that I know as long as epsilon's greater than something, it's also greater than this thing. So I'll show you what I mean. So I need to keep 2 over n squared plus 4 over n plus 3 minus 3. I need this less than epsilon, right? That I just rewrote exactly where we're trying to get.
So you're just going to work backwards.
Yeah, kind of. So simplify this real quick. I know I'll have shown that this is less than epsilon when I have shown that this is less than epsilon, right? So if I've shown this is less than epsilon, I've shown this. I'll have shown that if I've shown that this is less than epsilon using the triangle inequality. So if this is less than epsilon, this is less than epsilon, this is less than epsilon.
Where are you going with this?
I mean, I keep getting something simpler and simpler until I know for sure how to make that thing less than epsilon. So I'm basically just simplifying, only making my numbers bigger or the same. Bigger or the same. Because when it's all said and done, I may need my whole chain of things to be less than epsilon. When I make my biggest thing less than epsilon, then the whole thing is going to be less. I think you'll see better when I tie it all together. So this is equal to this, is less than or equal to this, right?
But it is equal to that, right? Not just by equal.
It's not.
Oh, wait.
In this case, it happens to be.
Okay.
But the triangle inequality only guarantees us that this is less than or equal to this. Now, this is less than or equal to 2 over n plus 4 over n. I made the denominator smaller, which could have only made this number bigger. N was either 1, in which case it's the same, or n was greater than 1, in which case this is bigger than this. With me? Which is equal to 2 over n plus 4 over n. The absolute value of those things is just those numbers. Probably should have done that a while ago. Which is equal to 6 over n. Okay? So that's as simple as I'm going to make it. So if I can get 6 over n less than epsilon, I'm good. So I need a force this to happen. I will have made 6 over n less than epsilon if I've made 1 over n less than epsilon over 6. By Archimedean property, there exists big N such that, well, exactly what I have right here. By the Archimedean property, I'm guaranteed that there is a big N such that 1 over big N is less than epsilon over 6.
Why not just, oh.
What does that mean? That means that then, well, all in one go, then 2 over n squared plus 4 over n is less than or equal to 6 over n is less than or equal to 6 over big N is less than epsilon for all n greater than or equal to big N. I found the big N. That makes this true, right? And if little n is greater than or equal to big N, this is also true.
Oh, right. Okay.
And we already showed that this is greater than or equal to this. That's what all this scratch work was.
It's quite a leap, but yeah. In the proof. If I could, in the proof, that'd be quite a leap.
Right, you'd explain it. You then put in this stuff. So we're doing our proof formally. I would do then this is equal to this, da 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 da, all the way to here. So all this, I guess I should have written this, oops. But all the steps in between you can then put in. But that's a hard proof. So therefore this thing converges to 3. Anything weird?
Did you that?
Yeah, that's fine.
And so n is just an arbitrary natural number.
N is just some natural number.
And
Greater than or equal to big N.
and big N is basically just
We found the big N that satisfies this.
right.
Big N is a natural number such that 1 over it is less than epsilon over 6. Whatever that natural number is, it satisfies this inequality. Therefore, every natural number bigger than it satisfies the inequality, etc. All the way back to here, that's just a different way of writing this. Therefore, this is less than epsilon for all n greater than or equal to big N.
So how?
Can we have a break?
Oh.
Yeah, once you understand this proof. Are we good with this example?
1 second. You look at the definitions. Minus a and a is 3. And that's how you know that it converges to 3.
Yeah. Our sequence minus a, if this absolute value, right here in our definition, if an minus a is less than epsilon for all, oh sorry, try it here. If an minus a is less than epsilon for all n greater than or equal to big N, then we've proven it. In our case, an was 2 over n squared plus 4n plus 3, and the thing we were proving it converged to was just 3. Good?
Good.
Okay. Yeah, we can go on break and then, I don't know, we could be done covering new material for the day.
So we're not going to talk about limits?
This is taking in a limit. We just need to prove that if something converges, it converges to one and only one number. And then we can define what that one and only one number is.
That's the
and that's what we'll call the limit. So far we have no proof that a series can't converge to two things. So we can't call the thing it converges to its limit. We need to prove it only converges to one thing, then we call it limit. So that's where we'll pick up from next time. Next time we'll re-go over the definition of a limit and continue right there.
So, the limit as n goes to infinity is, basically the thing that it converges to, but what about the limit as n goes to 0?
Good. So we'll get to that as we go to it. I realized I was writing these because I'm used to thinking about it that way, but actually it should have only been written like that. So right here we only talk about the limit of the sequence. Then when we start taking limits in different ways, we'll talk about the limit as n goes to infinity or the limit as n approaches any number.
So as far as that notation goes, you have the limit as n goes to something off your sequence, and that it represents.
There's only a limit of a sequence.
Right.
So I should have put that as n goes to infinity. It's when we start to deal with real value functions, when we can take the limit as it approaches any number, then we might also want to take the limit as it gets arbitrarily big as n goes to infinity. We'll explicitly define what we mean by the limit as n goes to infinity and the limit as it approaches some other number. We'll come up with explicit definitions for those.
But that actually represents a number, right? So the limit of a sequence represents a specific number.
If a sequence converges,
If it converges.
then its limit exists and it's one and only one number.
If it doesn't converge, then
The same way
is
that
undefined.
if a number isn't 0, then it has one and only one multiplicative inverse. If a sequence has a limit, or if a sequence converges, then it converges to one and only one number. And we call that number its limit the same way we call the multiplicative inverse of a if it's not 0, a inverse.
Right. Okay.
There needs to only be one of them for it to be defined. Otherwise it doesn't work.
So that's why. Okay.
Make sense?